Hello, let's talk some more about forces. First off, the weight force. Weight is equal to the mass of the object, which remember is an intrinsic property of the object. It's the amount of stuff it's made of, times gravity. And by gravity here, I mean the acceleration due to gravity, the free fall acceleration, which is 10 meters per second squared. So we have the force for weight, which is this equation, mass times acceleration due to gravity, little g. So this is part of how weight and mass are different things. So weight actually depends on the mass, but it also depends on this little g, the free fall acceleration. And that is different depending on where an object is in space. So for example, if it's near the surface of the Earth, it's that 10 that we're using. But if it's near the surface of the moon, it's much smaller because the moon doesn't create as much gravity as the Earth does. So I also want to look at this situation of a book resting on a table. The weight force that we just talked about, or gravity, the force of gravity, is pointing down, right? And if it's just sitting on the table, we know it's in equilibrium, which means there is no net force, or the net force is zero. So we have this other force counteracting our weight force. So the weight force points down, and then we have the support force or normal force pointing up. And normal here means perpendicular to the surface. So the surface of the book or the table 90 degrees from that is perpendicular. So this is called either the support force or the normal force. And it's just the force that you experience or anything experiences when interacting with another object and you're not like when it's like pushing back against you. If you push your hand on the wall pushes back, that's a support force. Now, one force we didn't talk about yet is friction. So friction is a force that results from the microscopic irregularities between surfaces. These catch on each other and impede or prevent the motion of the object. So we have like two, I don't know, blocks, one on top of the other, and there's friction between them. And we zoom in to those little imperfections on the surface, and we see that, when we zoom in, they can get caught on each other, which is what causes friction. Friction only occurs when there is motion or like an effort toward motion. We'll get to that in just a second. If two objects are sitting at rest, their surfaces are still like irregular. They're still all pokey or whatever. But there's no friction unless a change in motion is initiated between the surfaces. So unless a force is applied along the direction that they are in contact. So that would mean like if I started pushing on the green brick or block or whatever it is, like pushing it along the top of the blue one, that would produce friction. If I just push down on it, because the surface between them is horizontal, but if I'm pushing vertically down, that's not going to cause friction because it is not along the same axis as the surfaces themselves. So what happens is you apply a pushing force to an object, and then friction force occurs in response to that. So if you start to push on an object, the friction force is going to work to prevent that motion. And but also there's a point where you are pushing hard enough that you're stronger than that friction force. And then your object will start moving, but there's still a friction force. So let's look at this. So when an object is at rest, a friction force acts to prevent the motion. You have to overcome that friction in order to get an object moving. And that doesn't mean that friction goes away. It's just that you have to apply a force larger than the friction to get it moving because there's a limit to the size of a friction force. It depends on the materials that the two surfaces are made out of. So you can overcome it. But it depends on what objects are in contact with each other. And then once the object is moving, friction is still acting on it. So if you want to keep it moving with the same velocity, you have to supply a constant force to counteract that friction. Because remember, constant velocity or the same velocity means that there is no net force and no acceleration. So in order to do that, we have to have a pushing force that stays the same size as the friction force, so there's no net force. And I know that might be a little confusing because here I said, okay, you have to overcome the friction force to get the object moving, and then when it's moving, blah, 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 there's still a friction force. But these are actually two different friction forces. There's the first static friction force when an object is not moving, when the velocity equals 0. And then there's a kinetic friction force for when there is velocity, when the object is moving. And the kinetic friction force is smaller than the static. So you have to push harder to get something to start moving, but then once it is moving, you don't have to push as hard to keep it going at the same speed. Sorry, 1 second. But yeah, so for this example with keep trying to keep a constant speed, if your pushing force isn't equal and opposite to your friction force, you'll end up with a net force pointing in the opposite direction of your velocity. And if that happens, that means our object would slow down. So that's a change in the motion, change in the velocity means there's acceleration. Next up, I want to talk a bit more about vectors. We've talked about vectors. We've talked about how some things, some variables like velocity, acceleration, and force take into account how big something is and what direction it's going in. And we can represent that with what are called vectors, like vector diagrams, which is really just kind of like arrows or lines with arrows. So we have these two vectors here. There's, I don't know, maybe two different forces are being applied to an object or something like that. And we want to figure out what the the net force, overall force, or the resultant is. And to do that, we use the parallelogram rule, which it doesn't look like a parallelogram right now. It looks like a rectangle, but rectangles are parallelograms. But anyway, so you draw a dashed line to complete your parallelogram. So you draw a dashed line that is parallel to this vector, and then one that's parallel to the other vector. And then to find the resultant, you draw a new vector from where they meet to the other corner. So it's kind of like through the diagonal of your parallelogram. We're going to look at more examples of this, but just introducing the idea. So we have, we can look at an example of this here. We have this little girl hanging from a ring in the playground. The textbook calls her Nellie Newton. She's hanging in equilibrium. We know this because there's no indication that she's accelerating in any direction. And we have two force vectors that appear to be the same size and point in opposite directions. So that is also telling us that there is no net force, so she's in equilibrium. Although the upward force is a dashed line, so that's a little odd, but we'll get to that. And as with everything near the surface of Earth, Nellie is experiencing a downward pull of her weight force due to Earth's gravity. But we also learned that in order for acceleration to be 0, the net force also needs to be 0. So we have one force. I mean, the diagram has two, but we know what one of those forces is the downward force is her weight force from the earth. So what's this upward force that makes her in equilibrium? The upward force again is indicated by that dashed line, but there's not something that like follows along that dashed line. We don't know what force that is. There's a force that comes from holding onto a rope or a string. That rope or string will apply a force to a person or an object, and that's called a tension force. So Nellie is holding on to these two ropes. Those are both creating tension forces that she's experiencing, and those tension forces are what's counteracting the downward gravity force. But let's look at what that looks like. Like why does it look like that when normally a tension force, which I guess I didn't say yet, tension force moves along the rope or string. So there's no rope or string, at the dashed line. So why is that the direction of the force? Well, that's because it's the resultant. It comes from forces that act along each of the ropes and are turned into a parallelogram. And that gives us a resultant that counteracts the gravity force. So I think in this one we can see, so this is kind of working backward from that first example where we have the resultant because we know it needs to cancel out the gravitational force. And we can kind of create our parallelogram from that. And then that tells us what the two forces are from the ropes. So putting it all together, well, except for the resultant. But here's the parallelogram created and those two forces caused by the ropes. And the resultant is the one that we had, and that resultant cancels out with, there's the resultant, sorry, cancels out with the downward force of gravity, putting Nellie in equilibrium. Okay, let's look at another example of this. So first we have this snowboarder resting on a surface. And in this case, just like that book from earlier, the weight force is balanced by the support or normal force from the surface. And here that normal force is given by a capital N, and then the weight force is given by mg, where m is mass and g is acceleration due to gravity. So these vectors are the same size and in opposite directions, so the net force in this situation is 0. That's clear. But what about this situation? Our snowboarder is now on an incline, and we can see that like the normal force is still perpendicular to the surface, still 90 degrees from the surface, but now the weight force is not directly along that same line, so it's not canceling out. So this is where we need to create a parallelogram and find the resultant vector. So, sorry, it's all combined in one, but so we draw our dashes that are again parallel to the vectors we already have. And then we draw our resultant kind of diagonally through the middle, starting where our two original vectors meet and ending where their parallel sides meet. And so we see, okay, this snowboarder has a net force or a total force down the hill that they're on, which makes sense because we expect them to start skiing down the hill and all they're using is the force of gravity to do that. Let's look at another example of objects on an incline. But the incline is made of different stuff in each example. So we have ice. And ice is something that has a really low friction. It's very smooth surface. So lots of times a physics problem will say something is on ice to indicate that you don't have to worry about friction. And then we have this one where it's on like some wood or something, so there is friction. So if we look at these force diagrams, we have the normal force and the weight force. Those parts are the same. They're the same as the snowboarder, and that's on both of these. But then we also have for the not ice incline, we have this little f force pointing backward. That is our friction force. That it has to do with those like microscopic imperfections on the shoe and on the surface of the floor that are catching on each other. So this just tells us that the net force in these situations between the ice incline and the not ice incline are going to be different. So let's look at what it is for the non-ice incline. If we do the parallelogram rule just for two of these forces at first, if we just do it for the normal force and the weight force, we end up with a resultant of those two forces that points down along the incline. And the friction force points up along the incline. And what we find is because in this kind of situation, the shoe isn't moving, like that's part of the point of friction between like your shoe and something else. It's because the resultant of these other two forces is equal and opposite to that friction force. So the net force, the total force acting is 0. Whereas for the ice, because there is not that friction force going up, it does have a net force pointing along the incline, just like the snowboarder. So this person is going to slip on the ice. So let's do a few examples of these like getting the resultants from force vectors. So we have these stumps that are like have different forces acting on them. So let's look at each of them. And the first step is to draw the sides of the parallelogram. So there's one side, there's the other, and then we draw our vector from where our forces meet to the other corner. And so this is our resultant. This is the total or net force on this stump in this example. Let's look at the next one. So B, this upward force is much more angled than in A. So we have one side of our parallelogram and then the other side, which again is more angled because this force is more angled. And then our resultant force is longer, but also kind of doesn't go up as high. In our last one, we have this force that's all the way to our pointed more to the left. We draw our parallelogram and then we get our resultant vector, which has a rightward component, kind of like the part that points to the right, isn't as big as the last one because some of it cancels out by it being tilted to the left. Sorry if that part didn't make sense. Don't worry about it. Okay, let's look at it for these. And these ones are actually velocity vectors. So because velocity is also a vector, you can use the same process. So what these are is we have the vector of the plane's velocity, like just like that's where the plane's going. And then we have this wind speed. We have some wind acting on the plane. And so we want to know, okay, based on the plane's velocity and the wind velocity, what direction will the plane be flying in? And that is what our resultant vector is going to be. So first one, we have the two sides of our parallelogram, which is really just rectangle in this case. And then we see, okay, so it's going to go kind of up and to the left, or probably it would be like north and west. So that's the first one. The next one, we draw our parallelogram, and then we get our resultant. That one is going up and to the right or northeast. And we can see that the wind, because it's pointed up a little bit, pointed north a little bit, it gives us a boost to the plane. So like even though the plane is still not flying in that straight line, it is still flying a bit faster than it was. Then we have this one. This time it's probably not going to be as fast because the wind is counteracting the plane. So here's our parallelogram. And yeah, this resultant is smaller than that. And finally, we have these two. And this is a really extreme parallelogram. And yeah, we see a really big resultant vector. So this last one is pointed northwest, and looks like because the wind is giving the plane a boost, it's traveling the fastest because it has this biggest resultant velocity vector. Although none of them have the plane going straight, which is the direction it's aimed. So the plane would likely need to correct for the wind. Okay, that's all for this. Have a great day.